Hello everyone, welcome to Lesson 1 with me, JCat. We'll be talking about finding exoplanets, and maybe we'll find out if there's another Earth out there. First, let's start with why. The most important reason is that Earth will not be habitable forever. This will be discussed further in just a couple slides. Exoplanets are a great way to find data on how long our sun will last, how long our planet would last, what could happen to it. Some questions. Could we possibly find life? Could we find intelligent life? Their lifespans, that our sun will only last a certain amount of time. That Earth has about 5.5 gigayears, GY means gigayears, until it is no longer habitable. So what's next? Colonies. So in that 5.5 gigayears that Earth has to be habitable, we should have reasonably set up an off-world colony. And Mars is an example. This is an artist rendering, and the art creator is listed down here on the bottom corner. The planet Mars would become habitable in about 6.5 gigayears. So that's about 1 gigayear from when Earth is uninhabitable. But since the colony that is residing on Mars will be starting millennia ahead of year zero, they are at a distinct advantage of finding other worlds. Okay, simulations. Well, Okay, so as you see, the initial star mass is 1, so that means 1 solar mass of our sun. Our planet is 1 AU away. This is this little white bar indicates a distance of 0.1 AU. Our Earth is 1 AU away. So you see Earth is right in the center of this very comfy habitable zone. Now the real habitable zone actually goes out about here. It has a buffer from that solid line there to about here and to about right here, right where Venus is. There's a buffer zone. But this is the comfort zone. This is where we really want to be. Okay, so if we assess, it's about 100 Kelvin less than our sun actually is, but that's okay. So we can see down here, this is the Earth bar. So Earth is right in the center, as you can see above. And over here is when it becomes too hot, as you can see by the red bar. And then it has this straight down line that coincides with the star becoming a white dwarf, where it becomes too cold. So now we can run the simulation. I like to run it a little bit slower so you can really see it. It's not that slow. There we go. Okay, and run. And watch the very quick flash. And done. Now let's scale this bar back. Right here, when it becomes a white dwarf, between this time, you can see that its radius starts expanding. Then it goes pretty quickly. That habitable zone shoots very far out because the sun is going to get very big. And you can start seeing it the flash is so quick compared to everything else. And there we go. So the sun will come all the way out to Venus. And you see it blew Earth off its track. Of course, that also means Mercury will either be blown off or eaten by the sun, and Venus as well. But really, this shell right here would still affect Earth quite a bit. So the Earth will be blown off its track, as it's going to show, but it will also probably completely be destroyed. And the final is that Earth is all the way out here past Mars, and there's the tiny little habitable zone. Okay, what happens then? What happens after that? Well, after Mars, as I said earlier, they'll be starting millennia ahead, the span of from 6.5 gigayears to about 11 to be able to find exoplanets. So first let's establish a criteria. Over here, let's start with this. This is a lovely Hertzsprung-Russell diagram of stars. And right about here is where our sun is. There it is, right there. That's our sun. It sits right at 1 solar radius. Its brightness is somewhere between 10 to the third and 10 to the fourth. And if you go down right here, it is a G class. Okay, but what's this equation over here? What we use to find planets. So the N, which is what we're looking for, is the number of civilizations, with that could communicate with us. So how do we find that? First, we have to get the mean rate of star formation. We get that by looking at all the nebulae that we have around us. And then we have F sub p, which is the fraction of stars that have planets. Then we have N sub e, which is the mean number of planets that could support life. And let's see, right about there is where we have been able to determine so far. The rest of it, we have not. So we have F sub L, which is the fraction of life-supporting planets. That is the stage we're at right now in our search. Then really quickly, we have F sub I, F sub C, and L. You can read these right down here. But as I stated before, we are currently right at F sub L in our search. Okay, so getting Drake data. How do we do that? Well, one way is by sending telescopes and sending any type of data gathering device that can tell us what happened. So with Mars, the rovers are not trying to gather for future life, they are trying to gather past. Europa Clipper, on the other hand, which this slide reel will be uploaded on the Astrophysics 4, the number 4, all Discord. So anybody can look at it and click on any of these links. So the Europa Clipper, when it reaches Europa, will be gathering data on if Europa does have any habitability and life supporting. That is the F sub L that we are looking for. There's also another mission for Enceladus, but not really sure where that's at right now. Exoplanets. What does exoplanet mean? And yes, I have heard this question asked before. Any planet that is beyond our solar system. And in this lovely little image right here from Sci.News, that is an artist rendering of what TRAPPIST-1 is and which planets are too hot, perfect for water, or too cold. So, TRAPPIST-1 has 7 planets. However, their star is a K class, which is a red dwarf. They're small, and unfortunately, they excrete a lot of radiation, which makes these planets that could very well hold water strips their atmosphere quite regularly, so that's a little disappointing. So, how do we find what we're looking for? What are we looking for? Well, there is a way to simulate that. Using the planet data and the parent star data, we can simulate the radial velocity. And so, right here, because I've already done the simulation before, the example for option D is the Earth-like planet, whereas option 1 is the mass of Jupiter, one mass of Jupiter, but it's located where we are, so very close to its star. Run that option D then. Always check it. So inclination is 90 degrees. The solar mass is 1. Let's see, the mass of Jupiter. This is just about dead on with the mass of Earth versus Jupiter. You can see the fluctuation here. Now let's see that. You can see where in its orbit the fluctuation is seen. Then let's pause that for a second. Let's go all the way back to the beginning phase to restart. Let's show multiple views. So there's a view from Earth if we were at a 90-degree inclination. There's a side view, and then there's the orbit view. So look, 1 is right here. That's the side view. The Earth view would be 90-degree inclination right there, number 2. So as you can see, an Earth-like planet with option D with this very small mass compared to Jupiter, 1 AU distance from a 1 solar mass star would look like this. So what happens if we do make it a Jupiter-sized planet? I'll go to that option A, set. So we have 1 mass Jupiter, very close to its star with the same size star. You see how that radial velocity is much more dramatic. What happens if we make the star a little bit smaller? Half the size of our sun. You see the radial velocity changed over here. What if we make the star a little bit bigger? The radial velocity is now at 30 and negative 30 compared to 50 and negative 50. Let's just go back down to that. 0.5. See that? 50 to negative 50. But a larger solar mass and still close to it is a lot quicker. So, could a planet as large as Jupiter be terrestrial? Terrestrial meaning Earth-like, just very, very large. What are the necessities for a Jupiter-sized planet to retain gas. That little asterisk right there, that means keep that in mind for a little bit later. Okay, so transit simulators. Here's a little example, and then we will go to another simulation. Once a planet hits the outer rim of its star, just this little shell right here, that's when it starts to dip. You can tell how large a planet is, how close it is to its star, how large the star is by its dip. And as it reaches the other side, it goes back to normal. Okay, so transit simulator. This one's also very fun. If you get a chance to get on that Discord and find all of these, you'll think it's pretty fun too. So with this transit simulator, we are showing the theoretical curve. Make sure that's clicked right there. And if you assess this data first, let's see, the mass is slightly less than Jupiter, but the radius is larger than Jupiter. This is the planet. And it is very, very close in its orbit. Okay, the eclipse takes 2.93 hours and has a just over 3.5 day orbit. So let's slide this little scale here to show you just what I mean. Slide right there. It sits right at the edge of its star. That's where it starts to eclipse. And as it goes through its eclipse, it dips and starts to come back up, and that's the end of its eclipse. So what happens if we move this around a little bit? Now if you look, I changed the mass and the radius of the planet. It's still very close to its star, but the planet itself is slightly larger than Earth. I changed the mass of the sun to half mass of our sun. And I changed the inclination to 90 degrees. Now look at it. There's a very steep drop. This is because the planet is close and, relatively speaking, large with the sun. Watch it go back. Now what happens if we pull it out a little bit? It's not so close. Slightly over 1 AU. Now we see what happens. The eclipse depth, the hours that it takes to eclipse, and the orbit. 1.59 year orbit. So this is a lot of fun to play around with, and later on, if you are on Discord, you can come. Click on the link and mess around with this. So, as you can see, we can determine the AU, the solar mass, and the planetary mass and radius. As long as you have a few of those, you can figure out the rest. Now what? We found planets. We've determined their location, as far as how far they are from their sun. Now what? Well, can they retain gas? Gas retention is very important. We need 3 things at least to be able to host life, and that's oxygen, nitrogen, and water. So we are going to use 2 simulators. First we'll use the plot. Okay, so now that we have the plot pulled up, I have put water, nitrogen, and oxygen on the plot already, and ticked the little show gas giants. Jupiter is very high up, so let's see what we should be finding with the terrestrial planets. So we know Mercury cannot, Mars cannot, and Venus should be able to, but that also plays in with the habitable zone. So this is what we're really looking for. Now I have made this little planet, Earth. Radius, density, and temperature match. The actual temperature is 278, but this thing rounds up, which is still very close to our astronomical units. This is ideal. The temperature for a planet of this size and density over here. So why is Jupiter so different? Well, because the density is far less than Earth, and the radius is about 11 times more than Earth. So why do we need a planet like this? Well, because the gas retention is a lot better. So let's see if we move the planet just a little bit further out. Let's say 1.6 AU, which is about where Mars is, a little bit past Mars. And we can make this planet just a little bit larger, sub-Neptunian. Let's see, larger this way, yeah. Okay, that's about 2,500 kilometers larger than Earth. The density, just a little bit greater because the planet itself is a little bit larger. You see right here, it's starting to get a little too far away to be able to be categorized as a habitable planet. So let's see. At 220, so we'll take this temperature into the gas retention simulator. So as you can see, I loaded oxygen, nitrogen, and water, and set the temperature as the same as that planet at 220. Okay, now when I loaded that, let's allow escape. Let's see what 1500 would do by watching these meters right here. So as you can see, the levels are remaining mostly stable for a planet with this temperature at an escape speed of 1500 meters per second. Now let's stop this one and go check. So at this escape velocity, a planet this size and this close to its star would hold its gas well enough to support life. Okay. Well, there you go. We found out what our planet would need to be. Feel free to rewind, rewatch, share, and join the Discord.